Welcome to today's Explainer, designed especially for the grade 9 students at St. Paul American School Clark. Today, we're unpacking the exact production title G9 Geometry Unit 7 Lesson 7. Our focus? Scaling, similar solids, and dimensional effects. If you've ever wondered exactly how growing or shrinking a 3D shape impacts its surface area and total volume, well, you are in the perfect place. We're going to unpack the beautiful logical math behind all of this.
Okay, let's dive straight in. Here's our roadmap for unpacking the mathematics of scaling solids today. 1. Objectives of scaling solids. 2. The dimensional effects explanation. 3. Model applying scale factors. 4. Misconception, exponents, and dimensions. 5. Check, test your knowledge. And finally, 6. Recap, similar solids rules.
Section 1. Objectives of scaling solids.
So, let's establish our foundational definition. What exactly are similar solids? Basically, they are two solids of the exact same type that have equal ratios of corresponding linear measures. Think about things like heights, widths, or radii. If you compare the height of one cylinder to another, and then the radius of that first cylinder to the second, that ratio must be identical. That common ratio is what we call the scale factor, often represented by the variable k. And here's a really fascinating geometric fact for you. Any two cubes are always similar. The same goes for any two spheres. Because they're defined by just a single metric, like a side length for a cube or a radius for a sphere, scaling them guarantees that all their proportions stay in perfect lockstep.
Moving right along to Section 2, the dimensional effects explanation.
To really wrap our heads around these rules, we need to start small, like microview small. Imagine a simple unit cube. Every single side length is exactly 1 unit. Now, if we calculate the area of just one flat face of this cube, it's 1 times 1, which is just 1 square unit. And since a cube has 6 identical faces, the total surface area is 6 squared units. Simple enough, right? Now to find the volume, which is the space inside, we multiply length by width by height. 1 times 1 times 1. So our starting volume is exactly 1 cubic unit. Let's lock those numbers in our minds. Side length 1, surface area 6, volume 1.
Now, I want you to imagine taking that exact same unit cube and dilating it. Picture stretching it out in every single direction by a scale factor of 2. So our k equals 2. Every single one-dimensional measurement, every single edge, is now multiplied by 2. Instead of a 1 by 1 by 1 cube, we've got a 2 by 2 by 2 cube. Think about what happens to the surface area and the volume when we make that jump.
The math here brilliantly illustrates the dimensional pattern. When our scale factor is 1, our surface area is 6, and our volume is 1. But when we apply that scale factor of 2, look at the surface area. It jumps from 6 all the way to 24. It didn't just double, it multiplied by 4. Why? Because 4 is 2 squared. And check out the volume. It goes from 1 to 8. Again, it didn't just double, it multiplied by 8. And 8 is exactly 2 cubed. You could literally fit 8 of those tiny original unit cubes inside this new larger box. How cool is that?
All right, Section 3. Model applying scale factors.
Now, what's absolutely crucial to realize is that this isn't just some special parlor trick for cubes. It applies to all solid shapes. Take pairs of similar cylinders, for example. Even though these have curved surfaces and circular bases, the geometric rule is universally binding. If you double the radius and double the height of a smaller cylinder to make a larger one, the surface area will still increase by a factor of 4, and the volume will increase by a factor of 8. The shape changes, sure, but the math behind the scale factor remains absolute.
So let's build a repeatable procedure you can follow every single time. Whenever you're faced with similar solids, you just need these 3 steps. Step 1. Find your one-dimensional scale factor, your k. You get this by comparing any single line, like a height, a radius, or an edge. Step 2. If you need to find the new surface area, you must square that scale factor. Multiply the original surface area by k squared. And Step 3. If you need the new volume, you cube the scale factor. Multiply the original volume by k cubed. It is a highly efficient process once you lock in these rules.
Let's head into Section 4, misconception, exponents, and dimensions.
There's a really common trap you need to avoid here. Sometimes, when a shape is dilated by k, a student will try to find the new volume by multiplying the old volume by k squared. But we need to understand exactly why that's incorrect. Think about what these measurements actually represent. Surface area is a two-dimensional concept. It's like unfolding a cardboard box flat into a 2D net. Because it's 2D, we use the exponent of 2. Volume, on the other hand, is the amount of 3D space something takes up. Because we are measuring 3 dimensions, length, width, and height, the multiplier absolutely must have an exponent of 3. If you just link the word area to 2D and volume to 3D, you will never use the wrong exponent.
Section 5. Check. Test your knowledge.
All right, here's a specific scenario drawn right from our source material. We have 2 similar solids. We know their scale factor is 1 to 2. We also know the volume of the smaller solid is 216 cubic yards. Your mission? Find the volume of the larger solid. I'd highly encourage you to pause for just a second, recall those dimensional rules we just talked about, and try to calculate the answer yourself.
Okay, ready? The solution is 1,728 cubic yards. Let's walk through exactly how we get there. Our scale factor, our K, from the small solid to the large one is 2. But remember, we aren't looking for a 1D length, we are looking for a 3D volume. So we have to cube our scale factor. 2 to the 3rd power, which is 2 times 2 times 2, gives us a volume multiplier of 8. We then take our original volume, 216, and multiply it by 8. 216 times 8 gets us precisely 1,728. If you tried to just double the volume or multiply it by 4, you'd end up with a completely wrong amount of space. That K cubed rule is absolutely essential.
And finally, Section 6. Recap similar solids rules. Listen, if you only take away one core theorem from this entire explainer, make it this one. Commit this to memory right now. When any solid is dilated using a scale factor of K, all corresponding 1D lengths are simply multiplied by K. All 2D surface areas are multiplied by K squared. And all 3D volumes are multiplied by K cubed. This rule is absolute, whether you're dealing with a microscopic cube or a massive geometric pyramid.
I want to leave you with this final provocative thought. How do the exponents in our formulas perfectly mirror the dimensions of the space we are measuring? It's not a coincidence. It is the very structure of our physical world written in mathematical language. Once you see that 1 dimension requires an exponent of 1, 2 dimensions require a 2, and 3 dimensions require a 3, you unlock a deep, fundamental understanding of geometry that goes way beyond just memorizing formulas. Thank you so much for joining me for this explainer on scaling, similar solids, and dimensional effects. Keep looking for those mathematical patterns.